Hello and welcome to a lesson on GCFs and factoring by grouping. So in this short module we are going to review some factoring concepts. It's really something that you should be pretty confident and competent with at this point in your math careers, but lots of people factor different ways, and maybe it's been a little while since you've been in a math class, or maybe it's been a while since you've done any factoring. And whatever the case may be, because factoring is such an important and useful skill in just about any level of algebra, I thought it would be useful and helpful for us to take a couple of days to go through some of the factoring processes. That way we're all on track, we've dusted off all the cobwebs, and maybe you pick up a new skill that you maybe didn't necessarily have before. Okay, so factoring. What is factoring? If I say that to you, what does it mean to you? Okay, it's sort of the opposite of multiplying. So I'm going to start with this problem right here. Okay, if I asked you to look at this problem and I said to work that problem out, what would you do with it? Well, hopefully you would distribute, right? So you would multiply here, and the 2 times the 3 would give you 6, and then you'd add these exponents. So x squared and x squared would give you x to the 4th. You would multiply here. So 2 times 5 is going to give you 10, and you have x to the 2, and 1 makes 3, and then you would multiply here. So 2 times negative 4 would make negative 8, and you just have the x squared. Okay, so that is the multiplying process. You start with 2 polynomials, you multiply them out, use the product rule, multiplying, distributing, whatever you want to call that. That is the multiplying process. Okay, when you are factoring, you are working in reverse. So instead of starting with 2 polynomials, right? So here's a polynomial with 1 term, here's a second polynomial with 3 terms. Instead of starting with the 2 polynomials and multiplying to make 1 continuous polynomial here, we're going to be working in reverse. So in reverse is we start with the 6x to the 4th, 10x to the 3rd, and negative 8x squared, and we have to try to figure out what did we multiply to make that polynomial happen. That is the factoring process. That's where you start with 1 polynomial and you try to rewrite it as a product of 2 or more polynomials. Okay, so it's the process of rewriting 1 polynomial as a product of 2 or more polynomials. And you could think of it as, again, the reverse of the multiplication process, the reverse of multiplying polynomials. Okay? So that's sort of the idea behind factoring. Now there are lots of different factoring processes, but let's just dive into the vocab a little bit more. We've got the process of factoring, but let's back up a little further, okay? What does it mean for a number to be a factor of another number, or for a variable to be a factor of another variable? So for example here, if I said, what are the factors of 12? Could you tell me all the factors of 12? I'm hoping. Well, 1 would be a factor, so would 2, and so would 3, and so would 4, and so would 6, and then so would 12. So the factors of 12 are 1, 2, 3, 4, 6, and 12, and that is because each of those numbers divides evenly into 12. So a number variable is a factor of another if it divides evenly into it. Okay, so pretty easy to identify some factors of 12. That's a small number we're probably pretty comfortable with. What if I asked you to find factors of xy squared? Okay, it's a little more abstract, so let me take you to another example here. Let's say I wanted to list out the factors of 70. Now, I don't know if it would be as quick or easy to make the list like we did for 12 because the number's a little bit bigger. Not that you couldn't do it that way, but is there another way? Is there a process we could use to list out the factors of 70? In fact, there is. If we broke this down using a factor tree, let's see, 70 could be broken into 7 times 10, and then 10 we could take and break that into 2 times 5, so that we could say that the prime factors of 70 would be 2 times 5 times 7. Okay, so if I wanted to list out the factors of 70, if I was listing out the factors of 70, obviously every number is going to be divisible by 1 and itself. So those 2 numbers could go on the list. And now using the factor tree, I've also identified the prime factors of 70 being 2, 5, and 7. So I can add those to the list. And then the other factors, the other composite factors, are produced using the prime factors. If I take any combination of the prime factors and multiply, I produce another factor. So for instance, if I was to multiply 2 and 5, I get 10. Right? Then 10 has to be another factor. Or if I was to multiply 5 and 7, I get 35. That means 35 has to be another factor. Or if I was to multiply 2 and 7, I get 14. That means 14 has to be another factor. Okay? Now, it's not like you're going to be making factor trees to identify all the factors of numbers. In general, you're going to be able to figure out the factors that you're looking for. The reason I show you this process is so you can understand and visualize factors of variables. Okay, so let me take you back to the notes here. If I said to identify all the factors of xy squared, what are all the factors of xy squared going to include? Well, if we look at xy squared broken down, the same would be broke down to 70. What is xy squared really? Well, it's an x times a y times a y. So those would be like the prime factors, which means I could put x by itself on the list, I could put y by itself on the list, and then I could use any other combination of those multiplied. So for example, I could multiply x and y and say that xy has to be a factor, or I could multiply y and say that y squared has to be a factor, right? Or I could multiply the entire thing and say that xy squared has to be a factor. Okay, so that means x, y, xy, y squared, and then xy squared, all of those would divide evenly into xy squared. Okay, so that's the concept of a factor. Now, what we're really trying to do in this factoring process, in the beginning, in the first step in any kind of factoring, is going to be trying to identify and factor out a greatest common factor. So what does it mean to be a greatest common factor? Well, GCF, greatest common factor of a polynomial, is the largest number and or variable or variables that divide evenly into each of the terms in the polynomial, or whatever terms you're looking at in whatever situation. Whatever they all, the greatest common factor is going to be the largest number and or variable that divides into all of them. Okay, so let's look at 27 and 18. And I know I missed some blanks there. We're going to come back to them. 27 and 18, if I said, tell me what the GCF is, tell me what is the biggest number that divides evenly into 27 and 18, I'm hoping you can look at those and know that 9 is the greatest common factor. Okay, but what if the numbers were bigger? Let me again deviate here. What if they were bigger? Not ridiculous, but let's just say our numbers were like 54 and 84. Can you tell us easily by looking at those two numbers what the greatest common factor is? I mean, maybe. I don't know that I can, so is there a process? In fact, same process. We use a factor tree. So if I was to break down 54, let's say that it's 6 times 9, and then 6 can become 2 times 3, and this 9 can become 3 times 3. So then my prime factors would be 2 times 3 times 3 times 3. Now if I did this with 84, let's see, it's even, so 2 can go in 42 times. And that's 6 times 7, and then we could take the 6 and make it 2 times 3. So here our prime factors were 2 times 3 times 3 times 3, and then here our prime factors were 2 times 2 times 3 times 7. If we look at those lists and determine what prime factors they have in common, that product is going to produce the greatest common factor. So both of these lists have at least a 2. Both of these lists have a 3. Now this one has more 3's but the other doesn't. This one has a 2 and a 7, the other doesn't. The common factors, the common prime factors, 2 and 3, produce the greatest common factor, which is 6. So these 2 and 3's that they have in common tell me the GCF here is going to be 6. Okay? Now again, it's not that you're going to be making factor trees and having to do this process a bunch of times. In general, you're going to be able to identify what you need to without having to do this. But I show you the process so that you understand again what's happening with variables that aren't so easy to see, or that we're not so used to working with. Okay? So for example, x to the third and x to the fifth. What is the greatest common factor for x to the third and x to the fifth? Well, if I was to break these down the same way I broke down the 54 and 84, x to the third is really x times x times x, and x to the fifth is really 1, 2, 3, 4, product of 5 x's there, right? So if I wanted to ask myself what's the same on both lists, they have 1, 2, 3 x's in common. That means that the GCF here has to be x to the third, the product of those common prime factors, okay, x to the third. Now if I change this, let's say, to a 13 here for an exponent and a 15 for an exponent, then what would they have in common? Well, they would still have that smaller exponent in common, right? So the general rule is I don't want to have to make these factor trees every time. When you're looking at variables and the greatest common factor, the number of variable factors they have in common will always be the smaller of the exponents that you see. So x to the third and x to the fifth, they're going to have those 3 in common. Or if it was x to the 8th and x to the, let's say, 7th, then they would have 7 x's in common. Okay? So let me go back up to the blanks that we missed here. For any variables, then we want to use the smallest exponent that we see with those variables. And then 27 and 18, again, that wasn't too tough. 54 and 84, if I was looking at that and I couldn't see the greatest common factor was 6, then you could also use technology. So your calculator could probably do this, but since we're using Desmos, if you hit the function key in the corner here of the keyboard, function, and then you're going to, go to function and then hit miscellaneous, go to the miscellaneous tab. In the miscellaneous tab, you see where it says GCD. That's what the calculator calls greatest common factor. It calls it a greatest common divisor, which should make sense. If I wanted to know the greatest common divisor for, let's take that 54 and 84, if I type it into my calculator, it will tell me it's 6, so I wouldn't have to worry about making a factor tree. Okay? So the calculator can find the GCF for you as well. Why did I make that lowercase? I don't know. The GCF for you as well, but they just call it the GCD. Now, it won't do it with variables, but it will handle the numbers. So that was in Desmos. You wanted to go to the function, and then miscellaneous, and then GCD. Okay, that's how we got to that option to calculate that GCD. Okay, so hopefully we're feeling all right with this. Now, identifying the greatest common factor is one thing. Remember, the whole goal for what we're doing here is factoring. It's not just identifying a greatest common factor, but it's using that knowledge to factor our polynomial. So how do we go about factoring? Okay, let's jump down to this example number 5 here. By looking at those 3 terms, could you tell me what the greatest common factor is? Well, the biggest number that goes into 5 and 10 and 15 is 5. And if I'm looking at 3x's here, 2x's here, and 1x here, how many do they have in common? Well, the 1 is the smallest exponent, so 5x to the first would be the GCF. Now the question is, how do I use that to take this polynomial and factor it? Well, let me go back to the beginning here. Remember, what we're trying to do is the opposite of multiplying, okay? So if I looked at 6x to the fourth, change colors. If I looked at 6x to the fourth, 10x to the third, and 8x squared, and I said, what's the GCF? Biggest number that goes into 6, 10, and 8 is 2. And then 4, 3, 2, they have 2 x's in common. That 2x squared, that's my GCF. Once I know that's my GCF, that's got to be what goes outside of our parentheses. And then the question is, how do I figure out what's left over? Well, if factoring is the opposite of multiplying, it should make sense to divide, right? 6 divided by 2 gives me 3 here. If I have 4 x's, but I divide 2 of them out, then I've got 2 left. 10 divided by 2 is 5. If I had 3 x's, but I got 2 of them out here, then 1's left inside, and so on. So what we're going to do is I'm going to get rid of the million dots that I just put all over my paper. Okay, some of them. And let's go back. Not there. Okay, so let me go back. Here. We want to figure out what our GCF for the terms that we're looking at, and then we're going to write it outside of a set of parentheses. Okay? And to figure out what goes inside of the parentheses, we're going to divide. If we divide each term in our polynomial by that GCF, then the results of the division go inside of the parentheses. Write the results inside of the parentheses. And the nice thing about factoring is you can check your work. You know, if you were solving, you could check your answer by plugging in. If you're factoring, you can check your answer by multiplying. Multiply it back out and see if you got what you started with. Okay? And then just as a couple of notes here, the number of terms that you start with and the number of terms in the parentheses should always match, right? If you start with 3 terms and you divide all 3 of those by the GCF, then you better have 3 results that go inside of the parentheses. So the number of terms in the parentheses should equal the number of terms that you started with. And then the next 2 bullets we will come back to. Okay? So number 5 here, we identified the GCF as 5x to the first. So that's going to be outside of our parentheses, and now I have to divide. So when we divide the coefficients, 5 divided by 5 would give me a 1, which don't have to write, but if you want to put it there, you can. And then if I started with 3 x's, but I divided one of them out, that means I would have 2 left here. So a 1x squared or just an x squared would be fine. And then divide here. 10 divided by 5 is going to give me a positive 2. If I had 2 x's, but I divided one out, that means I'm going to have 1 left. And then negative 15 divided by 5 is going to make a negative 3. I only had 1 x. I pulled it out, so no x's with the 3. Okay, or more succinctly, 5x, and then x squared, 2x, and minus 3. Okay, if you really like the ones and you want to put them there, you can. At this level, I don't know if that's something that you're doing, but if you need to see it, that's totally fine. Okay, let's try that again. So looking at number 6, GCF, what's the biggest number that goes into 24 and 12? 24 and 12, not sure. Go ahead and use Desmos. Because if we don't take out the greatest common factor, then we're not going to be factored completely. So for 24 and 12, it's going to be 12. Okay? So 12 is going to be part of our GCF. Now there's 1x here and 3 here. That means they have 1 in common. And then for y's, we've got 4 here and 1 here. That means they have this 1 in common. So 12xy is my GCF. Now I've got to divide that out. So 24 divided by 12 is 2. And then if I get rid of an x and 1 y, I'm going to have 3 y's left. And then negative 12 divided by 12 is going to be a negative 1. And if I had 3 x's and 1 y, but I got rid of an x and a y, all I would have left here would be an x squared. And that would be my factored answer, right? We took one polynomial and rewrote it as a product of 2. And again, if you wanted to check your work, just multiply it, right? If I multiplied, there's my 24, there's an x, and then 1, 2, 3, 4 y's. And then if I multiply here, 12 times negative 1 is negative 12. 1, 2, 3 x's there all together, and a y, which is exactly what we started with. Okay, so you can always use a quick multiplication, which if you wanted to do in your head also, you can use that quick multiplication to verify your answer. Alright, so there's that. Now, let's look at a few more examples. Oops, not you, calculator. And again, we're going to come back to those bullets, but let's look here. So what's the biggest number that goes into 2, 4, and 6? That's going to be 2. How many x's do all 3 terms have in common? Let's see, 2 there, 1 there, 1 there, so 1x. And then how about y's? Well, I've got 2 y's here, 1 y here, but no y's in this last term, which means I cannot take out a y. There cannot be a y in my GCF. So we're just going to divide out the 2 and the x. So 2 divided by 2 is 1, and if I get rid of an x, I'll still have 1 left, and both y's will still be there. Next term, 4 divided by 2 is positive 2. Getting rid of the x, I still have a y. And then negative 6 divided by 2 is going to be negative 3 without the x. And there it is. Not so bad. Okay, if you're feeling good about this and you want to pause the video and give the next one a try, then go ahead. So let's see, 24, 18, and 12. What's going to be the greatest common factor? If you're not sure, 24, 12, and can I throw a third one in here? Yep, 18. Put all 3 in there. It still tells you the answer is going to be 6. So if you weren't sure, you could use your technology. So they're going to have a 6 in common. And then we've got 5, 3, and 1. So they have 1a in common. So 24 divided by 6 is 4. If I get rid of an a, I would still have 4 left here. 18 divided by 6 is 3. 3 a's minus the 1 that I factored out is going to leave me with 2 a's. And then negative 12 divided by 6 is negative 2 with no a's left, and that is your answer. Okay? Not so bad, hopefully. Alright, now if you notice something a little different about the next couple of problems, hopefully you do, the next few problems start with a negative. Now, the negative doesn't really change the GCF or the process of factoring out a GCF, but just as a rule, factoring out a GCF is usually going to be the first of many steps to follow. Usually it'll be factored out of GCF, and then we're going to continue based on how many terms we have left in our polynomial. And as we continue to factor, we don't want that first term to be negative. So whenever our first term is negative, we want to factor that negative out with the GCF. So looking at number 8, if I was ignoring this, let's ignore this for a second. The biggest number that goes into 4, 16, and 12 is going to be 4. And then I have 3, 2, 1, and 1x in common. So if that first term wasn't negative, my GCF would be a 4x, and I would divide it out, and no big deal. Because the first term's negative, however, I want to make my GCF negative. Okay, only when the first term is negative we'll do this, and it's more for when we continue to factor later. So we're going to factor out a negative this time. So negative 4 divided by negative 4 is going to give me a positive 1 in front of x squared left. 16 divided by negative 4 makes a negative 4 in front of an x. And then 12 divided by negative 4 is going to be negative 3 without any x's. Okay? So back to my first page. This is one of the bullets I left behind. When the first term of the polynomial is negative, then we're going to factor that negative out with our GCF. Okay? When the first term is negative. Any other term can stay negative, but that first one we don't want to. So looking at number 9. Biggest number that goes into 6, 18, and 6 is going to be 6, and because that first term's negative, we're going to factor out a negative 6. And it looks like we have 1x and 1y in common. So our first term, we're going to be left with an x and 2 y's. 18 divided by negative 6 is going to be negative 3, and then just a y left. And then the last term, negative 6 divided by negative 6 is positive 1. And sometimes we don't write the 1, but here we're going to have to, and hopefully you see why. We have to put the 1 here because the x and the y are both being factored out. And if we don't put the 1, we would have nothing left to hold the place of that last term. Right? When we multiply this back out, we got to be able to end up with the 3 terms that we started with. If that 1 is missing, then we would lose this last term. Okay, so if you have variables left, like here, for example, right here, I didn't have to put the 1 because I had an x squared to hold the place of that term. But if the variables both come out, you have to put the 1 to hold the place of that term. Okay? All right, let's try another one here. So number 10 is just to hit home this point. So if you're looking at 5, 3, and 2, the only thing that they're divisible by is 1. That's the only common factor they have, which isn't special because everything's divisible by 1. So if this was a positive 5, I would not be able to factor out a GCF. However, if the first term's negative, even if the terms have nothing else in common, we still want to factor that negative out. So I'm going to factor out a negative or a negative 1, and that's going to give me a positive 5x squared, a positive 3x, and then a negative 2 remaining. Okay, so we got to make that GCF negative even if it's just a 1. All right? Again, if you're feeling good about this, pause the video. Feel free to pause the video and give this a shot. So 14, 21, and 7 have a 7 in common, and because that 14 is negative, I'm going to factor out a negative 7. It looks like all 3 terms have at least 1x. So negative 14 divided by negative 7 is going to give me a positive 2 with 3 x's left. 21 divided by negative 7 is negative 3 with 2 x's left. And then 7 divided by negative 7 is going to be a negative 1. And again, I got to put that 1 there to hold the place of that term since no x's are left there. Okay? All right, so hopefully we're feeling pretty good. Now, number 11, 12, again, hopefully look a little different to you. If you're looking at number 11, your instincts might be telling you to distribute this back out, right? Give me an x squared here and a 2x here, and distribute this back out. But that's really not what we're trying to do when we are factoring. Factoring is the opposite of multiplying, right? So even though your instinct might be telling you to multiply this, we are factoring, and that is the opposite of what we are trying to accomplish. So remember, what we're trying to accomplish here in the factoring process up front is look for a GCF. So when it's a GCF we're looking for, we're asking ourselves, okay, what do all of the terms have in common? What's something that divides into all of the terms, right? So I guess my question in this problem would be, how many terms are we looking at? Okay, how many terms are we looking at? So I think it's pretty clear, like in number 10, how many terms we have. How many terms do we have here? Well, here's a term, minus here's a term, plus here's a term. Okay, so we've got 3 terms there. What about in number 11? How many terms do we have? Well, what separates terms is pluses and minuses, addition and subtraction. So technically, this x being multiplied by this x plus 2 here, that multiplication sort of links these together, which means this is all one single term. And the same thing here, the 7 is being multiplied by the x plus 2, so that multiplication does not separate those two, it links them together. So this is all one term. So all we're looking at in this problem is two terms. Now, can you see something that is the same in both of those terms? Well, hopefully you recognize that both of them have a factor of an x plus 2. So a GCF, it doesn't have to be a single term, right? It doesn't have to just be a 2 or a 5 with an x squared. It can be a binomial or a trinomial. It can be any size polynomial. So let me get rid of all this color here. I'm looking at two terms. If I recognize they both have an x plus 2, I can factor that out. So my GCF in this case is an x plus 2. Now, because it's more than one term, I want to make sure it stays together. So I factor out my GCF of x plus 7 in the same way I factored out my GCF of negative 1 or my GCF of negative 4. And then I divide it out to see what's left over and what goes in the parentheses once it's gone. So if I divide the first term by x plus 2, remember this is my first term here. If I take that whole term and I divide out the x plus 2, what's going to be left? It's just the x. So the x has to be here. And again, this term here, what's left, is going to be the plus 7. So x plus 7 is remaining. And that's my factored answer. Okay? This is all looking kind of ugly. So, oh, didn't want to change that. Change this guy. So our GCF, in this case, is a binomial. We factor that out. And then left over, once it's factored out, is the x plus 7, and that's what we put in the parentheses next to it. Okay? Just like the other problems, just the GCF is bigger. So let's go back to our front page and fill in that last little bullet point. So a GCF can be a monomial. That means it could be a single term. That's what we saw mostly in the beginning. But it can also be a binomial. It can have two terms. It could be a trinomial with three terms. It could be any size polynomial. If each of the terms in your polynomial has that thing in common, it's a greatest common factor. Or it is a common factor. Okay? So here, again, we've got one term plus a second term. And what do they both have in common? Well, they both have a 2x minus 5 in common. So I'm going to factor out that GCF of 2x minus 5. And then what's left over when I factor that out or divide that out? Well, what's left over? Oh, I'm so sorry. Going crazy with my pens here. What's left over is the 3x and the plus 4. So 3x plus 4 and done. Okay? And that process of being able to factor out a binomial, common binomial factor is going to be helpful for what we're looking at next. So let's say we're looking at problem number 13 here. If I said to factor out a GCF for this problem, is there something that all four of the terms have in common? In fact, no, right? The only thing that goes into 2 and 3 is 1. And I have x's here, 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 but not here. So technically, there's no GCF for these four terms other than 1, which again, not special. Okay? So what we want to do is instead of looking for a GCF for all four of the terms, I'm going to put a line here. This is not going to mathematically do anything to my problem, but it's just to help you separate the two groups. So instead of looking for a GCF for all four terms, let's just look at the first two terms, and then let's separately look at the next two terms. If I was just looking at the first two terms, what do these two have in common? Well, they've got a 2 and an x squared in common. So I'm going to factor that out from those first two terms. Okay? If I factor that out, it's going to leave me an x here and then a plus 1 here. Now what about the second group? What do the last two terms have in common? Well, they have a positive 3 in common. So if I factor out the positive 3 from those two terms, what do I have left? Well, I have left an x plus 1. Now, have I changed my problem at all? Right? By splitting into two groups like that and looking at them separately, have I changed anything? Well, no, because here I still get the 2x cubed and the 2x squared plus the 3x plus the 3. So it's exactly the same problem I started with, but we're one step closer to being able to factor. Right now, we're in the situation we were with problems 11 and 12. Now, instead of 4 terms, we've only got 2. And what do the 2 have in common? Well, they both have an x plus 1. So we can factor out that x plus 1. And what's left over is 2x squared plus 3. So 2x squared plus 3. So even though there wasn't a GCF for all 4 terms, we were able to find a GCF for the first 2, another GCF for the second 2, and then we were able to find a common binomial GCF. So we call this process grouping. And this is a process that we're going to apply anytime, or we're going to try to apply anytime we have a polynomial with 4 terms. Instead of looking for a GCF for all 4, let's look at this into 2 groups, the first group and the second group, and try to factor out what they have in common. So this is a process, again, this is called grouping. We use this when we have polynomials with 4 terms. So I use a line to separate the 4 terms into 2 groups of 2. Now I don't know if that's a mathematically correct thing to do. You don't have to put anything there at all. It just makes it a little more visual for me. It's just to say, okay, let's look at the first 2 separate from the last 2. And we're going to factor out the GCF from each group. Okay, and that's going to allow us, that's where we end up in this step here. Once we factor out the GCF from each group, what we're going to see from there is a binomial GCF. So at the second step, they had an x plus 1 in common. So we're going to factor out that binomial GCF. And then what's left over when we factor it out was the 2x squared plus the 3. We put that as a product next to it in parentheses. So write the remaining terms, which again were the 2x squared and the plus 3, in parentheses as a product. Okay, so let's try this again. Now, don't write this yet because it's not going to be correct. If I split this into 2 groups, maybe you're recognizing something weird about this one anyway. In the first group I can take out a 2, which would leave me a 3x cubed minus 1. In the second group I can take out an x, which would leave me a 3x minus 4. Not really helpful here if these binomials don't match. So this didn't work for us here. Does that mean that I'm not going to be able to factor this problem? Actually not, and maybe you recognize this. You probably did, but there's something different about this polynomial. We want to make sure that our terms are in order before we try to factor, and that's going to be true for any factoring problem. So we want the terms to be in order. So put the terms in order before we try to do any kind of factoring. So the 6x cubed is where it should be, but we should be following it by the 3x squared, and then the minus 4x, and then the minus 2. Okay? So now that it's in order, let's try to regroup here. First 2 terms have in common a 3x squared. If I factor that out, I'm left with a 2x and a plus 1. Second group have in common a negative 2. So I'm going to factor that out, and that's going to give me a matching 2x plus 1. And now these 2 terms have a 2x plus 1 in common, so I'm going to factor it out, and what's left over is 3x squared minus 2. So that goes next to it in parentheses as a product. Boom. Okay, we factored. We took one polynomial with 4 terms, and we were able to rewrite it as a product of 2 polynomials. And again, if you wanted to multiply to check your answer, you don't need to do this every time or on paper, but here's the 6x cubed that we started with. Here we see a negative 4x, that's over here. Let's see, here we have a 1 times 3x squared, so 3x squared, that was here. And then, I need another color, the 1 times the negative 2, we've got the negative 2. So multiplying this back out produces the same 4 terms that we started with. Okay? So let me... Alright, there it goes. Let's try again. These terms are in order, so let's go ahead and split this into 2 groups. First group has in common a 2 and an x squared. If that's factored out, we're left with an x and then a minus 6. Now the second group, what do they have in common? Technically the only thing they have in common is a positive 1, and although we don't normally do this, I'm going to go ahead and put the positive 1 there because I can see these x minus 6's match, right? I know that's what I'm going to be factoring out next, but I put the positive 1 so that I can see that that's still going to be part of what's left over once the x minus 6 comes out. So x minus 6 gets factored out, and what's left over is the 2x squared and that plus 1. Okay, so even if they have nothing in common, let's put a plus 1 there just so that we don't lose any of our terms. Alright, so if you're feeling good about this, again, one last chance for you to pause the video and give it a shot. Otherwise, let's see. First 2 terms have in common an x squared. Factoring them that out is going to leave us an x minus 3. Second group has in common a positive 2. Factoring that out is going to give us an x minus 3 again, which is good, because now that matches in both of those. So now we can factor out that x minus 3, and what's left is x squared plus 2. And there it is, we've factored. Okay, we took one polynomial and rewrote it as a product of 2. So again, hopefully this is stuff that's looking familiar, or at least we've dusted off some cobwebs. This is sort of like a real small intro into some other factoring processes that we'll see. But work through the practice, and if you're still struggling, need a little bit more, then reach out. I am here to help. All right, guys, take care.